Hello and welcome to this video. In this video we're going to be looking at graphical motion. Now what I mean by graphical motion is not that how the graphs move. What we're saying is up to this point when we've described motion so far we've only looked at forces, right? But we know there are things like speed, velocity, acceleration, displacement, all of these other values, and we know that as something is moving those values can change. So if we're just going to use numbers to be able to explain how something is moving, we need to use a lot of numbers. Now when we have a lot of numbers it's usually easier to use a graph. So what we're going to say is now we need to be able to map specific motions onto specific graphs. Now there are three types of graphs that we have. And the first type is a displacement time graph. Okay, so the key here is that this is displacement, right? So this is a vector, which means I can get both positive and negative displacements. Okay, depending on how you set up your axes at the beginning of the question, which way you define to be positive, which way you define to be negative, is going to tell you whether your displacement is positive or negative. Now, I'm going to take a simple example in this case. I'm going to say that something is traveling with a constant speed, okay, starting at the zero displacement, and then over time it just gets further and further away in the positive direction. Okay, so I'm not actually going to worry about this negative for now because this is my zero. So I start at this point and then I'm moving like this. Now I said this is at a constant velocity, but how would I actually be able to say that I know, if I was given this graph in an exam, how would I be able to tell that this is a constant velocity? Well, whenever we have graphs, there are two main things that we need to look at that are going to tell us something. Well, three for the most part in physics, but for these graphs we're going to look at the two main things. And we need to look at usually the area, that's usually going to tell us something, and also the gradient. Okay, now as a side, also the y-intercept. Okay, so sometimes in physics, and what we'll see when we take graphical analysis of more things, sometimes we do just want to work out what the y-intercept is, but all of these things will tell you some sort of information about this. In this case, the area underneath the graph is just going to be a displacement multiplied by time. Now that doesn't give us any values because if we take a displacement and multiply it by time, we just get units of meters seconds and we have nothing that's in units of meters seconds. Okay, so your area for this means nothing, but your gradient is the displacement over time, right? This is displacement over time, and we know displacement over time is just velocity. So the gradient of a displacement time graph is velocity. Okay, now what if I had have drawn something where it's curved? So I know it's a constant velocity here because it's a constant gradient. This is a fixed gradient, it's a straight line. If I drew a different type of motion, let's say I had something that was more like this, the gradient of this is changing as time goes on, which means we don't have a constant velocity. And so we have to be able to then map how does the velocity change over this amount of time. Okay, so now let's look at velocity time graphs. Okay, so y-axis is velocity. Again, I can get positive or negative velocity because it is a vector. And let's use this as an example. So let's say, let's assume that this is some sort of quadratic. And so the gradient change is going to be constant. Okay, now this isn't going to be something you have to worry too much about. They're not going to ask you to specify how much it's changing, but it is useful to have some grasp of these kind of concepts. So what we could say is at zero, at time t equals 0, our gradient is something like this. So we have quite a high gradient, which means we're starting off with a very high velocity. And then over time, it's gradually going to decrease and it becomes 0 at some point. So really what we're saying is if this change in gradient is constant, like I'm assuming it to be, then I'm going to get a constant constant change in the acceleration, okay, until I reach 0, because my gradient when this displacement time graph is flat is 0, okay. Now again, I've neglected the negatives for now just to simplify things, but there are examples that we're going to look at in this video that will take into account negatives. Now, what is the gradient and the area for this? Well, the area underneath this, right, so let's say, let's actually make a list under each of them. So for a displacement time, the area means nothing, but the gradient is the velocity. In a velocity time graph, the area underneath this is velocity multiplied by time. Now, if we had velocity is displacement over time and rearranged it, we'd see that velocity multiplied by time is actually just displacement, which means the area under this curve or under this graph is the displacement. Okay, but also the gradient is how the velocity has changed over time, and we know the change in velocity over the change in time is the acceleration. So the gradient of this is also a value. Okay, so the acceleration, which brings us on to our third thing. How do we map how the acceleration changes over time? So let's go slightly this direction. And so if this is our velocity time graph, remember our acceleration is also a vector quantity, so we're still going to have positive and negatives. So we have acceleration against time, okay, where this is time and this is acceleration. Now, if the gradient of a velocity time graph is an acceleration, that means that the gradient here is fixed and the gradient here is negative, which means we have a constant negative value for your acceleration. Okay, so this is where the negatives are going to start coming into play here. Because this is a constant gradient, we get a constant acceleration. Okay, most of the time, since we're looking at usually at things like gravity accelerating something, it will be a constant acceleration because it's always going to be the gravitational acceleration, which is a constant close to the surface of the Earth. Which means there that if we have graphs like this, we should be able to map a displacement onto a velocity and then a velocity onto an acceleration. But then let's see what all of these things mean again. So if we had the area under an acceleration time graph, we've said that if, so we know the acceleration is the change in velocity over the change in time. So if I multiplied the acceleration and the time, I'd get the area. So the area under here, so in this case it's this area here, is actually the change in velocity. I'm just going to call it delta V to save space. So it's the change in velocity. And the gradient, if I had acceleration divided by time, really means nothing. Now I'm going to put something in a different color here because there is a quantity that can be explained by this, and it's called jerk. Okay, so this is just for enthusiasts. If you wanted to know what the rate of change of acceleration is called, it's called jerk. We don't really go onto the rate of change of jerk because by the time we get down to jerk already we're looking at constant changes. Okay, now to continue with this aside, those of you who are doing maths will probably recognize that this, to get the gradient of a curve at any point, you probably want to differentiate it. Okay, so this is going above the physics knowledge and applying a little bit of maths to this as well. It means that to get from displacement time to velocity time, we're differentiating. We differentiate that again to get to acceleration. And if we wanted to go the other way, we'd be integrating to get to velocity and then integrating to get to displacement. Now this doesn't matter too much, okay? If anything, this is just a cool thing that you can relate now between maths and physics. But what is interesting, even if, well, because of that, but for those of you who aren't doing math, what you could still see is that if we do the gradient, we're actually going this way, right? So the gradient of a displacement time goes to velocity, the gradient of velocity time goes to acceleration, and the gradient of that would go on to jerk as well. But if we do area, we're actually coming backwards. So the area of an acceleration time gives you velocity, the area of velocity time gives you displacement, okay? And this is the key concepts. We need to be able to know what does the area under each of these mean, if it means anything, what does the gradient of each of these mean, if it means anything, and how could we actually use one graph to be able to represent a different type of graph. So if we knew the displacement, how would we then be able to get the velocity graph? This is going to come into play in both years. Okay, so your first year stuff, just looking at this AS mechanics topic, is going to go through a lot of this, but then also when you come to do your further mechanics, that is also that will be after your AS exams, we'll do this again, but we'll do this in terms of trigonometric functions instead of just straight lines and curved lines. Okay, now let's take one example to be able to show you how we would determine what the motion of something would look like if it's displacement at time. My example is going to be, I am going to take a ball from the ground and I'm going to somehow fire it straight up vertically, and when it goes straight up vertically, it's going to stop at the top, and that's going to be, that height is going to be 2 meters tall, okay? And then after it does that, it's going to fall down, and then it's going to hit the ground, and it's going to come to a complete stop. And what I'm going to draw to begin with is a displacement time graph. Okay, now displacement time, I have to define which direction is my positive. So I'm going to define the upwards direction is the positive direction. That means if this part here is my 0 in displacement, I'm starting at 0. Okay, now I'm going to go up to 2 meters height, so I need to mark where my maximum is going to be. However, in order to get up to that point, we need to see what this line is going to look like. Is it going to be a curved line? Is it going to be a straight line? Is it going to curve up or down? Is it going to do some squiggle to get there? And what we need to figure out is basically how does the rate of displacement change? How does the velocity actually change? When we first start off, the velocity is going to be a maximum, okay? Because we're kicking it up, it's just going to start accelerating towards the sky, okay? But we know near the top, the velocity at the top is actually going to be 0. So I'm going to say velocity is maximum at the bottom when we just kicked it, and it's going to slow down, which means our gradient needs to start off as a maximum and then fall to 0. So it's going to look something like this, right? It's going to be a curve. This should be more zero-y, but you get the idea. Then from here, the actual motion starts to fall. So our displacement is going to begin to come back down to 0. Now, again, we have to think, if we were to now start this as being velocity is 0 and this is maximum, right? So it's, even if we flipped it around and went in the opposite direction, it would still be the same, because we'd start with 0 and it's going to accelerate downwards until it reaches the maximum. So that means that we're starting off flat, and when we actually hit this, we want the gradient to be as large as possible, okay? And so really all we're going to do is just keep going with this, and then it stops there, because we said that it's going to hit the ground and then come to an immediate stop, okay? And this makes sense, really, because it just means that over time the ball is going to go up and then come straight back down, okay? And this is okay. But what we now want to do is take this idea and try and map this onto a velocity time graph. Okay, so we're going to get this. And how would we change this kind of curve into a velocity time graph? How does the velocity change as we throw something up and down? Well, we said initially it's going to have a maximum point, and then finally it will come to a 0 around here. So it's going to go to a 0 there, and then this here is going to be a negative maximum. Okay, so let's first look at this, and then we'll worry about the negative maximum in a second. So in order to get that this was a curve here, we looked at the velocity and how the velocity would change as we move up. In this case, the way our gradient is going to change is going to be entirely based off the acceleration. Now, for this whole thing, the acceleration is due to gravity, because this is a vertical motion. The only acceleration we have vertically, assuming we have no air resistance or anything like that, then all of our acceleration is due to gravity and it's going down, okay? Now gravity is a constant, okay? Which means if gravity is constant, our gradient here has to be constant. So in order to get from this maximum point to this minimum point here, it has to be a constant gradient. And in order to get down to this minimum point that we're going to have here, it needs to continue being a constant gradient. Now this obviously looks like it's bent in the middle, but it would be a dead straight line, okay? Because the gradient of this should be minus 9.81, and then this is going to be meters per second squared, because it's meters per second divided by seconds. Okay, now it should be negative because we've defined upwards to be positive. We know that the direction gravity works in is always down towards the earth, and so that means that this gradient should be negative. If we were then going to take this and map it onto an acceleration time graph, okay, like we've just said, this is going to be constantly minus 9.81, so our acceleration will look something like this, where this is always going to be minus 9.81, okay? So this is our example of if we were to throw up a ball and just let it hit the floor and then it will stop. So we'll get an arc. So what you can usually do with this displacement is kind of imagine how the thing is actually changing. So imagine it's moving up and then it moves down, and then how quickly is it going to move up and how quickly is it going to move down. You'd get your displacement one pretty easily. The velocity is just going to be taking the gradient of these points, and then your acceleration is going to be taking the gradient of your velocity graph. Okay, so this is the graphical analysis of all of these motions. I would suggest probably thinking up some kind of motion, maybe falling, maybe bouncing a ball a couple times, maybe a yo-yo if you want to make things interesting, and then just try and replicate as many different types of graphs that you can. And then I think with practice you'll get the hang of this, and it will also make reading them much easier because you'll know how to draw them, which makes reading them kind of just the backwards. Okay, so hopefully this all makes sense, and thank you for watching.